Hello. Today we are going to talk about low observables characteristics of modern combat aircraft. Now, most of the modern combat aircrafts now have similar performance from different designs. So, what distinguishes them from one to another is how well they are able to camouflage themselves, how well they are able to reduce the observables, like their acoustic or visual observables, or through radio cross section, through reflecting radar waves and things like that. So that's what we're going to talk about now. Going forward to the next slide. So any study of military aerodynamic configuration development should include stealth now. It's become imperative across all the designs because it plays a key role in survivability and configuration layout. So survivability in the sense that the enemy defense systems take a little longer time to uh, recognize the incoming aircraft if it has been designed to have the characteristics of stealth. And because stealth characteristics cannot be an add-on after the aircraft has been designed, it also impacts the configuration development right from the beginning. So the point is, if they want to have characteristics of stealth built into an aircraft, it has to come from right up from the beginning, from the scratch. It has to be designed like that. And importance of stealth cannot be overstressed because it directly impacts the survivability of the aircraft and the pilot within that. Most of the missiles which are being used by countries are becoming smarter and also more reliable. So there is no such thing as too much stealth, and you will always be now detected. And all best you can hope to achieve is to delay or reduce the time gap they have between detection and activating their defensive mechanisms. So most of the techniques about stealth are classified, have been classified over a period of time from both the original designers, but certain basic principles have been described and can be, of course, addressed even at the classroom level. And stealth itself is usually considered to consist of several elements. It's not only the radar reflecting capability, it also has other capabilities. All these are called signatures of the aircraft. So radar cross section, not to be confused with the actual geometry, is called RCS. And there are things like infrared, visual, and oral meaning acoustic, visual, and infrared things. So all these things are kind of signatures of the aircraft. So the reduction or other control of an aircraft's radar, infrared, visual, acoustic signatures can greatly improve its survival, resulting in improved weapons effectiveness. In the sense that if you're going to send your country's bombers and everything else into the enemy territory to deliver bombs or missiles, and if your detection is late, then of course your effectiveness is better. So it's not only your survivability and safety of the aircraft, it also improves the effectiveness of what it's supposed to do. So although radar stealth is important, overall the observability is critical as well. So the control of signatures allows aircraft to achieve higher exchange ratios and improve survivability. Exchange ratios meaning a one-on-one or multiple n-on-one kind of encounters. Then of course you can improve your survivability even in those circumstances. This will allow the destruction of highly protected targets without unacceptable loss, in the sense that some of the key installations of the enemy will be protected by what are called point defense systems, radars, and anti-aircraft missiles. So if you can delay or take a little longer for the enemy defensive mechanisms to detect you and activate themselves, then the chances of you achieving the targets are much better. And the loss in terms of you being shot down, the aircraft being shot down, is also minimized. So while remaining undetected gains time to plan and execute the optimum attack. So that's the whole idea of reducing. You cannot, of course, eliminate and become completely invisible. That's a fairy tale. All you can do is reduce your signatures. So low observability or stealth is one of the most misunderstood or misinterpreted concepts. In the open literature, you have things like invisible aircraft and things like this, which of course is not true. Stealth aircraft are not invisible. Unfortunately, they also can be detected by radar. Only thing is that you delay detection as much as possible while undertaking covert operations. Delayed detection gives enemy less time to activate defense, and by which you improve your survivability. In simple terms, stealth technology allows an aircraft to be partially invisible to radar or any other means of detection. All it can do is reduce the detection range for an aircraft, just like jungle camouflage worn by soldiers. So this camouflaging techniques is not new, it's existing in nature. The stripes you see on the Royal Bengal tiger is because when it moves inside jungles with tall grass, its green and yellow stripes bodies kind of merges with the background. Even this kind of camouflage paint schemes were used in the aircraft even during the World War II. So most of the aircraft were painted like blue and white when they seen from the bottom, and painted green and yellow on the top of the aircraft. So if the aircraft is watched from another aircraft which is at a higher altitude, the target aircraft would kind of merge with the ground in the sense of green and yellow kind of things. So these kind of things have been used even in other older technologies, and of course it's been pretty common in the nature. You would see many animals and insects, for example, even a grasshopper, when it sits on a bunch of leaves, it's almost undetectable. Of course, you do detect it, but it takes a little longer for you to detect a grasshopper sitting on grass or on leaves than it would be, for example, if it was yellow colored or some other color. So the most critical electromagnetic signatures are the primary means of detection aerospace vehicles right now, in the sense the kind of radars which were of course introduced during the World War II, and the story is that they were installed at Pearl Harbor, and the radar systems did detect the Japanese incoming aircraft, but they were ignored by the local commanding officers because this was a new technology, and people generally have a tendency to mistrust new technology. I said electromagnetic signatures or reflected radar signatures, so just one of them. Other signatures are also important, though less critical. For example, acoustic, the noise. When a fighter plane comes overhead, you hear the ear-splitting noise. Okay, of course, when it is over the head, it's easy to detect, even visually, that is optical. And when it is, of course, at a distance, it may take you a little longer to detect it if it's not that noisy. Okay, and another signature is the infrared or the thermal signature. This is very important if you are being chased by missiles, which most of the missiles, anti-aircraft missiles, both launched from ground as well as launched by another aircraft, have infrared seekers, meaning that they home on to any hot source. So if you can reduce the infrared signature of your jet exhaust, of course, obviously in an aircraft, most of the present aircraft are turbojet kind of aircrafts, turbofans and turbojets, and their exhaust is very, very hot gases. So if you can try and control that, then of course you have a better chance of survival against incoming infrared seeking missiles. Let's spend a couple of minutes and looking at each one of the kind of signatures. Acoustic signatures of an aircraft generally between 2 centimeters and 16 centimeter wavelengths are due to the aerodynamic noise from the vortices coming from the wings and the rotors and propellers and engines. Overall, there are different kinds of sources of noise. So the intensity of noise is directly proportional to the wingspan loading and speed of an aircraft. So the reduction of such signatures contribute towards acoustic stealth, but as we all know, the wing loading and the span loading is an important parameter as far as the aerodynamic performance is concerned. So there's not much scope or leeway for us to fiddle around, only from the acoustic reduction point of view. But however, that's one of the options which can be looked at. Sound attenuation is inversely proportional to the wavelength square. This makes low frequency noise an important factor for acoustic stealth, which means that if the frequency is low, its attenuation is very, very low, so it can be detected easily. So this is one aspect which can be addressed. Optical signatures are quite obvious, of course. The size and shape of a vehicle are important factors for detection by optical signatures. The contrast against background is crucial in fixing the threshold of detection. So the background luminescence depends on the atmospheric conditions and the target position with respect to the sun. So if you have noticed, sometimes when the aircraft is flying overhead, there is a reflection, or what is sometimes called the glinting of the aircraft, where the aircraft's body reflects the sun's rays. So this could be one of the ways it can be detected. So the surface texture, I'm sorry, of the vehicle and atmosphere, reflected illumination are other factors that decide the strength of optical signatures, which vary from zero point 0.4 to zero point 0.7 micrometers. Thermal signatures or infrared signatures vary from zero point 0.7 micrometers to 1 millimeter due to the heat generated by the aircraft engine jets, propellers, and rotors. And of course, the exhaust heat from the aircraft is the largest source of infrared signature, and can be, of course, sometimes if you are being chased by a missile, if the engine exhaust engine can be kind of hidden from the missile by traveling towards the ground, so that when the missile sees, it doesn't see it directly, it sees only a part of the engine's exhaust, because the exhaust is now pointed upwards since the aircraft is flying towards the ground. This path divergence, as it's called sometimes, enables reducing the detection probability of the aircraft by detectors at the ground base or even on the aircraft base. Moreover, low emissive materials, for example, AG or AL, can be used to avoid detection. But of course, here too, there are limitations on what material can be or should be used in the nozzles, exhaust nozzles. There's not much leeway there, but sometimes it can be thought of. Engine exhaust should be screened by other airframe components if possible. In cases, the surrounding fuselage does kind of shield the exhaust directly, in the sense that the nozzle is slightly inset in the fuselage. Another technique we used, which can help, is the modern bypass engines. Basically, if you're looking at a low bypass turbofan engine, you can't use high bypass turbofan engines, because by nature high bypass turbofan engines have a large diameter in the frontal cross section, and they are not very useful for combat aircraft. Since most combat aircraft engines are actually buried inside the fuselage, and diameter of the engine becomes a crucial thing. So all said and done, one does look for a low bypass turbofan engine. So the advantage of a low bypass turbofan engine is that the air which is coming from the bypass part is relatively cooler compared to the main engine exhaust, and this kind of envelops the hot exhaust jet coming from the main engine. So this can, in one way, reduce the infrared signature. The crucial part we are going to look at is radar signatures. Radar signatures generally come from 3 millimeter to 30 centimeter wavelengths. Signatures are related to radio frequency emissions from aircraft. These are primarily reflected RF signals and can be reduced by either applying radar absorbing material coatings or shaping the aircraft. Of course, it's not as simple as it's said here. There's a lot of science and technology goes into both shaping the aircraft as well as different kinds of paints and materials which can reduce. Of course, the key point here is special attention should be given to the hotspots, including the edges and corners of aircraft. It's been known the radar reflection is kind of amplified whenever it hits a corner or a right angle corner, for example. Then the reflection backwards is very, very significant. So the idea is to try and minimize edges and corners, or even if they do have edges and corners, try and make them parallel to each other so that there is some kind of overlap. Other part is to ensure that no surface of the aircraft is illuminated by radar signal at normal incidence. Okay, it's quite an obvious thing. For example, you shine a torch at a mirror directly perpendicular to it, the whole light comes right back at you. The mirror reflects the whole optical light back. Now, if the torchlight hits the mirror at an angle, you do get some part of the light reflected towards you, but a large part of the light is reflected away. So this is an analogy, not to be taken word for word. So the same way, if they ensure that the radar signal coming from either from the ground-based systems or from the enemy radar, because nowadays missiles too have their own little bit of radar in that. So if the radar signal does impact any surface on the aircraft in the normal incidents, then of course most of it is reflected back to the receiver. So this means that either there are two options which have been followed. Either you have very, very smoothly merged surfaces like a B-2 bomber, or flat faceted surfaces like F-22. So, and similar to that, signals incident at smaller angles, vertical surfaces, just fins, become significant contributors. So, if you see some of the modern aircraft, if they have two vertical tails, they are canted, meaning they are not parallel to each other, they are at an angle to each other, just to ensure that whatever radar wave comes from the side is not reflected back. You should, of course, avoid corner reflectors type geometry, since surfaces meeting at right angles give rise to strong radar return. So these are all, the basic principles which have to be followed. And how they are implemented in actual aircraft design is, of course, another thing altogether. It's not as straightforward as it sounds, because the designer is always having a dilemma in the sense there is a trade-off between trying to minimize radar reflection, also ensuring that there's not too much of compromise, especially in the aerodynamic performance. So these two are contradicting requirements. So there has to be a trade-off, and then some kind of an optimal solution is derived given the constraints. May not be the best, but given the constraints, you have a reasonably good aerodynamic performance and also reasonably low radar signature or radar cross-section. So let's look at how exactly the detection happens because of radar. When a radar site transmits signal and measures the signal that is returned from the target. In this case, basically, you send out a signal, a wave, radar wave, and we assume that the radar wave is planar. Of course, it's not. But as in a first approximation, we can assume that there's a planar wave incoming towards you. And when it hits the target, three things happen when an electromagnetic wave hits an object. Three things normally happen. One, reflection. Second, transmission through. And the third is absorption. So, for example, even if you look at a conventional or a normal day-to-day mirror, because the mirror is kind of, given a silver coating on the back side of the glass, most of the light it is reflecting. So you are able to see your face. If you look at it, almost 90% of the light is reflected back. You are able to see it. Now, if that coating is not that good, there is some amount of transmission through that as well. So, even on the other side, you can see. You can see through it. So these are the things which are called one-way mirrors and all that. So as I said, absorption happens, and so local heating happens, reflection happens. So depending on the nature of the wave and the kind of material, one of the three things will dominate. It will either reflect most of it back, or reflect most of it away from the things, or it will let it through. For example, you shine a torch through a plain glass, most of the light goes through. You shine it on a mirrored glass, then most of it is reflected back. Okay, or if you shine it on a one of the ground glass kind of thing, most of the light is scattered and neither goes through nor reflects back. So there is a source, which source is generally, if it is a ground-based source, they point out the radar waves are directed towards the sky at a certain angle, and whenever there is something reflected back, it is received. So the earlier systems, the transmitter and the receiver were co-located. Okay, and this was the usual case, and the radar is known as monostatic in the sense that the transmitter and receiver are at the same place. Of course, there is a modern or a slight change in that possible. If the receiving antenna is located elsewhere, not at the place where it is transmitting, then it becomes bistatic. Okay, now this bistatic scenario increases the complexity of our stealth design because you don't know where exactly is the receiving antenna. Now, if it is a monostatic unit, then the receiver is also in the same direction from which the incoming wave is there. But if it's bistatic, then of course you don't know which way, where is the receiving antenna, and that means that you really don't know what to do or how to ensure the scattered waves don't reach the antenna. So this is a little increased complexity. So what you see in the picture here is a very, very highly simplified schematic, or you can almost call it a cartoon. And you can see here, a thing that which sends out a radar transmission, and it comes out like this, and this triangle-like thing is an object, and you can see part of it is reflected back, part of it is reflected away from that. So the reflected waves, the ones coming back to the transmitter, that depending on the strength of the incoming waves, you can of course judge what is the size of the aircraft as well as how far it is. So all the idea of stealth or low observable design comes in to minimize this part of the reflected waves and maximize the part which is scattered away rather than in the direction which is coming. So of course this becomes increases the problem if it's a bistatic thing. While I may design an aircraft to minimize the reflected waves going towards the transmitter, the receiver may be somewhere else. For example, in this case, if I know, of course, where if you know where the receiver is, then you can also alter the design of the aircraft or missile, whatever is your object, so that reflection doesn't go in that direction. But of course, since you're not aware where the radar receiver is, it becomes a difficult thing to do anything about. Now, a transmitter literally is shouting its place. Whenever a transmitter transmits a wave, it is actually telling you where it is because that is its detection. But a receiver is passive. It's not transmitting any wave, it's just receiving. Then it becomes very difficult to detect that. Generally, we have heard of radar cross-section. So it's expressed as an area. It's a ratio. Okay, and it not to be mixed with the geometric area. So 1 square meter is the reference area, and the value of the RCS usually expressed as a relative value using decibels. Okay, so in the sense, this is the equation. So sigma meters by 1 meter and a log of 10. So basically, it is in comparison with a known object at a known distance, and compared to that, what is the cross section of the present aircraft. So some typical values of radar cross sections. If you look at classical bombers, the B-52s or the older generation bombers, B-7, B-52 and things like this, then their radar cross section is close to 1,000 meters squared. Okay, of course, it's not a frontal cross section or anything. It is just a radar cross section, as I said. It's not geometric. It's 1,000 meters squared. Classical fighter planes like the Spitfire in the World War II, Spitfire and other things are like that, and they have something like 100 square meters 100 square meters radar cross section, and of course now slowly that's been being reduced, and as I said earlier, the flat surfaces in the incoming wave should be avoided and all that kind of thing. That's the thing. Now, so most of the modern aircraft, like Tejas or Rafale or thing, they are the radar cross section 1 meter or even less than that. Okay, so less than a meter is what we are being aiming at now. Typically, if you take a bird, its radar cross section is 0.01 meter square, and an insect is 0.001 meter square. They just to give you a flavor of the kind of numbers we are talking about in radar cross section. These numbers are nothing hard written on stone. So you just understand that the modern aircraft, so your in the radar cross section is 1 square meter or less than that. Most of them are less than that now. So as I said in the beginning, it's not always possible to reduce the radar cross section in all directions because you really don't know where the receiving antenna is and because you know where the transmitter is. It's not easy to detect where the receiving antenna is. So what is done at best is to try and minimize in certain areas where you think possibly there is going to detection happen. So in this picture, as you see, let's assume this triangle as the object we are trying to design stealthily, not design stealthily, include stealth characteristics. So if you take a 45-degree angle from this front sector, so this will cover whatever radar wave coming from the ground, as I show here, from the ground stations, or from AWACS. AWACS are early morning, aerial aircraft which stay at a very high altitude, also detect incoming aircraft. So generally, the front sector, plus minus 45 degrees, is something which you would like to try and minimize the radar cross section. The other part is if you're being chased by a missile or the AWACS above but behind you, or missiles, then the rear part, 45 plus minus 45 degrees, is important in terms of both rear sectors. Often, these of course, more important thing here is infrared, meaning the exact exhaust. And to the extent possible, side ones are tried, you try to minimize them. Of course, you cannot always minimize everything. It's impossible to do that. So most critical, the front sector is wings, okay, and the cavities. Cavities, meaning there are other lots of cavities on an aircraft which are used for different purposes. The largest cavity, of course, is the inlet, which needs to feed the air into the engine, which is inside the fuselage. So you will find that the inlets, air inlets for the combat airplanes have become a very critical aspect in terms of reflecting waves. So, for example, even as most of the children, if you have seen, they take a cap of a pen and then blow air just above it, and then it sort of resonates. So the point I'm trying to make is waves have a tendency to amplify and become larger in amplitude and in direction when they go through tubes and cavities. So this is something which, of course, you need to have air inlets, and which need, because you need to have the air coming into the combustion chamber and the turbojet engine. But you can try and see how we can modify the air inlets to minimize its reflection capability. And a simple equation itself, of course, it gives you a little bit of insight as to how important RCS is. The simplified radar equation is P suffix R, which is the power received by the antenna, is equal to a constant, which of course you have to find out, and multiplied by RCS, multiplied by the transmitted power, P suffix T, divided by distance to the power 4. Okay, so the ground station transmits radar waves with a power of P suffix T. The target aircraft or a missile is at a distance R, and its RCS is known, multiplied by constant is the amount of power received by the antenna. Okay, so PR received by the detector depends on RCS, of course, directly, and the distance to the power 4. Basically, distance is very crucial thing. So all I want to do is reduce the power received by the antenna. For that, I can, of course, reduce the RCS, okay, and ensure that my RCS is so low that I am not detected until my R is significantly smaller than earlier. Since detection and activation of defense depends on power received, reducing it will benefit the attacking aircraft. So whenever there is a radar station, there are radar operators, and they are trained to look at the blips which come on their screen, blips coming in from reflected things. So with their training, they are be able to practically identify the kind of aircraft. They will certainly know the number of aircraft, because that is directly proportional to the number of blips which come on their screen. And of course, from the size and the speed at which it's expanding in size, they will be able to know the distance at which the aircraft is. So just look at a simple example. Consider two aircraft, A1 with a radar cross section RCS1, and another aircraft A2 with an RCS where RCS2, where RCS1 is 1/16th of the RCS2. So you're having two aircraft, one some radar cross section, the other one is 1/16th. In such a situation, if aircraft 2 is detected at a distance of 100 kilometers, the aircraft 2, remember, has a larger radar cross section. If it can be detected at a distance of 100 kilometers, then A1 can be detected only when it is 50 kilometers from the radar. Okay, so it can really sneak in much closer to the target before it's being detected, only because its radar cross section is 1/16th. You see here the amount of reduction needed in radar cross section is very, very significant. 1/16th RCS reduction is not a small thing. But of course, if you do that, then you can sneak in within 50 kilometers of the radar, and by that time it will be too late for them to. So this is a highly simplified example, but illustrative of the importance of RCS reduction. There's not much you can do about the constant, which comes from the all other physics part of it. Only way, if they have to detect your aircraft at 100 kilometers with reduced RCS, the only thing they can do is increase the transmission power. That means if they increase the power of the radar transmitter, then they can detect even the smaller aircraft, smaller RCS aircraft at a higher distance. Okay, on the ground-based systems, it is possible to increase the transmit power because it's not much worried about the weight and stuff like that. But if the radar is being carried by an aircraft or by a missile, then the power transmit possible is limited. Of course, it's limited by the weight of that system. So what are the major contributors for reflecting the radar waves? Metals have a tendency to reflect most of the RF waves, and metals are there in compressor phases. For example, engine compressor phase from the forward direction, turbines from the aft direction. So if there is a radar wave coming from the back, then the turbines reflect it back, and if they are compressor phases, then they are from the front radar. Another thing is, because these are rotating devices, there is also a Doppler shift in the radar which comes in, so that will help the radar detecting systems to be able to identify systems. Air inlets for engines and stores meaning whether they are bombs or missiles, which normally are carried inside or carried under the combat aircraft, and they also have other missiles themselves have seeker heads. So all these are possible reflectors. So wing from directly below or above leading edge, especially if it is unswept, has a very big radar reflection possibility. Of course, in most combat aircrafts now, sweep is almost given. There's not much of a significant part, but it is clear that a rectangular wing will reflect most of the radar waves compared to a swept wing. Corner reflections at intersections of horizontal tail and vertical tail are very, very crucial. So that's the reason, as I mentioned earlier, some of the modern fighter planes have vertical tails which are canted. Canted meaning they are not parallel and they are facing in different direction. I think they have a picture somewhere. We'll see that things. Radome and bulkhead, if transparent, to illuminating radar. So if radome, the front part of an aircraft, they too need to have a radar. Most aircrafts have radars. They also do emit waves. So these two can be detected easily. Bulkheads are the structural components. Cockpit, including cavity effect, so when the RF comes in, the glass panel which is there in front of the pilot, of course the radio waves go through right there, but then they act like a cavity inside in the the pilot's cabin, and then the cavity can amplify it and send everything back again. And engine nozzles, as I said, if viewed from the rear, flat slab-sided fuselage when viewed from the side. So these are possible areas where one can try and make some modification to reduce radar cross sections. Incidentally, it's possible to numerically estimate the radar cross section. It may not be exact number, but it will give you differences if when you make changes in the geometry. So incremental changes in radar cross section or incremental reductions can be estimated by numerical methods. Of course, this is not testable in a wind tunnel. You need to have a different setup for actually testing it if you want to do experimental testing. So there are smaller but also important contributors, because when you're trying to reduce the radar cross section from 1 square meter to 1/100th of that, then you do have to look at all possible sources. So fuselage in head-on view, if we can try and modify that, wing leading edge and control surface gaps which cause scattering. Control surfaces in the leading edge, of course, are the slats, maneuver slats, and things like that. And whenever there's a moving surface, there has to be a gap. Otherwise, there is fouling. So these gaps can act as an amplifiers, which then, of course, need to be addressed. Local air inlets, for example, for cooling and air conditioning, they also act. You may have taken great care for the engine inlet, but there are smaller inlets which are needed, sometimes locally to cool equipment. Long, thin fairings, for including missiles, which are usually snug under the wing, they are also something which you need to look at. Vertical and horizontal tails I've already mentioned about, and all other protuberances you want to remove, or smoothen them out or flatten them out so that they don't reflect. So, methods of RCS reduction, there are two basic approaches. There are two major approaches to shaping an aircraft to reduce its radar cross-section, or RCS, as it's usually referred to, using a compact, smoothly blended external geometry to achieve a continuously varying curvature. For example, in the SR-71 Blackbird, and of course in the V2 bomber, or using a faceted configuration, meaning with flat surfaces to minimize normal reflections back to the illuminating radar. For example, YF-117 and DASA Firefly or DASA Firefly. So the faceted design example is shown here. Notice the flat angular surfaces, unlike any other aircraft normally you would see, which will have a smoothly blended surfaces, smoothly curved surfaces. In this case, you see a lot of flat surfaces. These flat surfaces are not designed arbitrarily. Each one of them, there is a lot of care needed to design the flat surface at the angle in which it is placed towards the thing. And you also notice that the vertical tail at the back is canted. Okay, so this is one design. And if you see also from the front side, the air intake is actually canted backwards and is also on top of the wing. What this does is reduce the RCS for an incoming radar wave, especially which is coming from the ground. Most of the ground-based radar stations transmit their radar waves at an angle to the horizon so that they don't get scattered by the existing buildings and things like that. So an aircraft flying at around even an altitude of 5-6 kilometers, if the air intake is above the wing, this is not exposed to the RCS. Why this is so, we will briefly talk about it a couple of slides down the line. On the other type of design, as I mentioned, is smoothly curved things. If you look at this is the B2 bomber, and observe the smooth surfaces and also the parallel edges, both the trailing edge and the leading edge and parallel edges. But also, as before, see the air intakes which are on top of the wing. Now, if you look at any other existing combat airplanes right now, whether it is a MiG series or Mirage series or F-16s or even our own Tejas, the air intakes are always below the wing. One of the reasons most of them is below the wing is the aerodynamics on top of the wing is very, very crucial in terms of performance. And you don't want to have extra protuberances and stuff over the wing. But however, in the stealth designs, the design requirement is totally different. So that is why these things, they have an air intake which is above the wing. The radar cross-section reduction methods, or RCSR methods, there are different techniques. What most of the designers do is try and locate the radar spikes or the zones from which the aircraft is returning a large amount of incoming waves. So what is done is actually to reduce the number of spikes by concentrating on as many similarly aligned reflecting surfaces as possible. Reflecting surfaces which are similarly aligned ensure that there is minimized reflection. For example, we'll talk about this in another case, YF-23. Incidentally, Y indicates that it's still in the prototype form. The accepted aircraft will have a different numbers, it's only F attached to it. Similar to this is all the panels on the underside of F-117 are hexagonal in shape. The panels which cover the wing and fuselage. Every line on the underside is thus parallel to the trailing edge of the wing, which ensured that any return would be minimal in nature. A similar approach is also adopted in F-22. Then comes the issue of intake, what we did refer to earlier about why air intakes on stealth designs are placed over the wing, not under the wing. So if you look at a simple straight air intake's main job of an air intake is to convey the air from the front right into the engine face. So what you see is the shaded part is a very rough depiction of an engine, and what you see in front is the air intake. But basically it's a tube which slows down the incoming air and passes it on to the engine. So the intakes in F-14 and F-15 were excellent aerodynamically, but it was realized from the stealth point of view they were not very efficient. The reason being, as seen in the simple picture, the darkened part is the engine, and the first part of the engine which is encountering the incoming radar waves is the compressor blades, and compressor blades being metal blades, they are excellent reflectors. So whatever wave comes right into through the intake hits the compressor blades of the engine, and then they are returned back. So this obviously is not a very good idea if the intention is to reduce the radar reflection. If the intention is to improve the aerodynamic performance of the intake in terms of minimizing the total pressure loss or avoiding any kind of secondary flows, this design approach is excellent. So one way to try and reduce the intake is what's called a serpentine intake, as shown above. What this does is, as you can see, there's no direct line of sight for the incoming wave to the compressor blades. Of course, the radar waves do get reflected internally in the duct, and after multiple reflections do reach the metallic blades, and then when the metallic blades reflect it back, they again go through multiple reflections, and hopefully they are attenuated by the time they come out of the inlet and reach the transmitter or receiver, whatever it is. So this is one of the techniques used, but this poses a few challenges in terms of aerodynamics, because whenever the flow goes through double bends or single bends like this, there are bound to be secondary flows along with that, and of course also total pressure loss. So the main aerodynamic challenge is to ensure that the line of sight for the compressor blades is not there from the intake phase, but at as low a loss of aerodynamic performance as possible. Several attempts have been made to try and minimize the secondary flows by having vortex generators inside, and different kinds of techniques have been followed. Another major area where electromagnetic waves are reflected back are from the cockpits and radomes. Most of the aircraft themselves have radar transmitters for several other purposes. These two are dead river waves, and cavity lighting which is formed in the cockpit also acts as a huge reflectors. So if you look at the side, if the radar wave is hitting the aircraft from the side, the convention aircraft, as you can see on the left, of course it's a very simplified depiction of a circular fuselage with a vertical tail, which is the standard configuration in most of the aircraft, let's say the passenger aircraft or even the conventional combat airplanes. Now when the radar wave comes from the side, what happens is it hits the vertical tail, and most of it is reflected back towards the transmitter. And the same thing happens with the curved shaped fuselage. Now this can be attenuated. So as I said, you can't eliminate the whole thing. What can be done is to attenuate the reflection by shaping the fuselage. What you can see is that, of course, you don't really make it into a square cross section. What is being depicted here is some kind of faceting is done on the side of the fuselage, as well as the vertical tails are canted so that one doesn't see rectangular intersections. Of course, as you may have noticed in the B-2 bomber, they have completely done away with the vertical tail itself. The horizontal tail, the job of the vertical tail is done by a complex sequence of events using ailerons and other things, but then there's no vertical tail at all. So this is a design thing which is usually done in stealth design. And if you look at the F-117, there are some similarities you can see. I've tried to point out a few of them. For example, the trailing edge of the horizontal tail is actually parallel to the leading edge of the wing. And the horizontal tail itself is not a nice rectangular thing, it also has a shape. And you can see the other shape of it is parallel to the trailing edge. So this, as I said, this edge is parallel to this part, and this part is parallel to another thing. So as you can see, the whole thing, if you see from this side, all you see is kind of aligned parts. So great care has been taken to ensure that this kind of similarities are ensured in this. Of course, when this is done, F117 of course has vertical tails, but that they are canted. These of course pose challenges in the aerodynamics part, which we will refer to a little later down the line. So a little more detail on F117. No right angled tail surfaces, they are canted, they are no longer parallel, swept wings, and no external stores. All these stores, even though it's a compact airplane, all the stores like missiles, bombs are housed inside the fuselage. So there is nothing sticking out of them. So whenever they need to be released, there is a door-like thing which slides back, and the store is dropped down and then fires. This has its own problems, but just to reduce the scattering of the back scatter of the radar waves, all the stores are carried in-house and they are flush inside the fuselage. And engine intakes are also cornered, so they are no longer straight intakes, and you can see the engine intake is cornered, the canopy is shielded, angled plates with parallel edges to control specular reflection. Specular reflection means like light rays, so that kind of thing, and also radar absorbing material covers all the surfaces. So all these things make this a very expensive aircraft, and also a difficult thing to fabricate and produce. This is not something you can manufacture in hundreds. So the other design is the B-2 bomber, which as I showed you earlier, contains a smooth surfaces. So what you see on the left is the original design. You have a straight leading edge, and you have a straight trailing edge, and one cut back in this direction. Later it was realized that this part of the trailing edge needed to be modified, and you can see that there is a cut in the trailing edge of the wing. It comes like this and goes back. And as before, this part of the trailing edge of the wing is parallel to the leading edge of the wing, and this part of the trailing edge is parallel to this. So, and similarly, this part is parallel to the leading edge of the wing. You can also see multiple control surfaces here, because this is there is no vertical tail, and the yawing functions need to be very carefully managed using these kind of control surfaces. So that is a challenge which needs to be attended to. So intakes have sharp faceted face also, and are placed over the wing in order to avoid ground-based radar detection. No vertical tail to reduce side deflection from a bistatic radar, because you need to ensure that while you are reducing the radar reflection from the frontal or the monostatic radar, the possibility that the bistatic radars are there. So you also want to minimize that reflection for vertical tails from the side transmitters or side reflections. So there are general, thumb rules in trying to control the radar cross section. One is reducing the size. This is a valuable addition to reducing RCS. The overall size of the aircraft is reduced, then the chances of reflection are lower. It's we can say it's almost intuitive. It's a lot easier to look at a huge object compared to a slightly smaller one. Using swept leading edges is one of the techniques where the radar cross section is reduced, but unfortunately excessively swept wings can produce performance, stability and control problems. As very high swept wings have issues with landing velocity, their stall velocities will be higher. So other issues are there. So there are problems related with performance, stability and control, and there needs to be a kind of a trade-off between what you're trying to do, reduce the radar cross section at an acceptable reduction in performance and control. So other technique is avoid vertical surfaces altogether, but if not feasible, cant them so that the surfaces avoid right angle corners, the kind what you saw in F-16 or even now in Sukhoi, you can see the same thing. Carry stores including fuel internally You house them internally, and as and when needed, if it's a disposable store, there is a sliding door which opens out, and the store is dropped. It's a missile or a bomb. Fuel, of course, can stay inside. These aircraft rarely, or if at all, carry drop tanks. Then it's probably avoided at any cost. So that would be a dead giveaway. Minimize and eliminate control surfaces, but that is not feasible completely. For example, the F-117 and Y-23 use radar vectors, which are actually a combination of radar and elevators. Tejas, as you know, it's called elevons, which are elevators and aileron combination. In this case, this is radar and elevator combination, or radar vectors. F-22 has dispensed with a dedicated speed brake, because that would have been thing. Eliminate the cockpit transparency cavity by treating the transparency with a thin conducting layer. For example, F-16 uses this technique. Use a clean external geometry with minimum protuberances, aerials, inlets, doors, gaps. All this need to be attended to, and as we'll talk about it later, all this adds to the extreme cost of such aircraft. Bury engines with air inlets and exhaust located over the upper surface of the airframe to mask the cavity from major ground-based illuminated radar threat. Of course, it's not necessary that all the radar illumination happens from the ground. Nowadays, we have what are called AWACS, or early airborne warning systems, which can stay at very high altitude and keep a track of all incoming hostile aircraft, in which case, of course, the radar illumination happens from the ground. So the inlet duct giving it a S-shaped duct, meaning basically a double bend serpentine, can hide the compressor phase from incoming radar waves and force multiple reflections on the ram line diffuser. The idea is more reflections on radar observing materials, better is the attenuation. That's the idea. So giving it a S-shaped or a serpentine duct will automatically increase the number of reflections and attenuate the outgoing ray. So there's just a pictorial representation. You can see the intake duct has a certain amount of bend, and of course there are thumb rules about how much could be the bend without triggering secondary flows and all other kind of things. But also the intake phase, the inlet phase, or inlet intake phase is also canted backwards and forwards, sometimes sideways, just to ensure that the incoming wave is taken care of. But as you're aware, when these aircraft reach supersonic speeds, the shocks formed on the intake phase can have adverse effects if they are not properly designed. So there is a trade-off between designing the intake phase for supersonic flow as against what we need to do for reducing the radar cross-section. Coating and absorbers, another thing which are passive. Surface alignment is very important for external surfaces, inlet and exhaust edges. The returns from inside the cavity is heavily dependent on the attenuating material, basically the kind of material you use for coating. Radar frequency range from range of interest covers between 2 to 3 orders of magnitude. You are not sure what kind of radar frequency is coming in, and their frequencies could be 2 to 3 orders of magnitude. Permeability and dielectric constant are two properties that are closely associated with the effectivity of attenuating material. This is where the challenge is posed. For a coating to be effective, it should have a thickness that is close to the quarter wavelength of the frequency of interest. Okay, now if you know exactly the enemy's radar frequency, then you can design your coating to be around the quarter wavelength. But as indicated earlier, radar frequency range has a wide range in 2 to 3 orders of magnitude, and this is a challenge one needs to attend to. So there are very considerable with frequency properties varies happen. So it's not always that you just paint with the radar material and then it does the job. And that is not so. The thickness has to match the incoming frequency of interest. The other part is the radar illumination of the rear part of the aircraft, and that is where we have engine nozzles. While of course engine nozzles, the major issue there for the observable is the infrared reduction, but one needs to attend to radar cross section also. The problem with these is if you can coat the nozzle walls with this radar absorbing paints, but because of the very high temperatures which nozzle walls are subjected to because when the engine is running, there are issues with the adhesion of the coatings. Because basically these coatings have some kind of property. They can have a different thermal expansion compared to the base material. So the structural integrity becomes a very, very big issue. In the sense, these coatings can simply peel off because of the temperature and the differential expansion seen by the material, the base material and the coating. So that is a challenge. But anyway, there are issues. People have tried the coatings on the nozzles. And generally the nozzles are also tried to be shielded by body components around them. But again, the high temperature and the exhaust temperatures ensure that the body which is trying to shield it is also capable of accepting the temperatures. Just an example of what has been achieved. For example, the traditional Eurofighter, an older design, is supposed to have an RCS of about 1 square meter. Whereas F117 with all the modifications we suggested it has been implemented, is reported to have an RCS in the interval 0.001 to 0.01. So 1000 to 100 of the Eurofighter's design. And as I pointed out, this can reduce the detection time by the opposing or enemy radar quite significantly, but it comes at a very, very heavy price in terms of cost and production and all that. So the requirement for aircraft to be stealthy results in very unconventional configuration, because you are at the same time addressing observables, acoustic, optical, infrared, radar cross sections. And these throw up a lot of performance issues, production challenges, controllability, maintainability. All this pose a number of unknowns. So, for example, this kind of coating, as I said, effective only if the thickness is one-fold the incoming radar frequency. Now, if the radar frequency is changing, obviously, as I say, one size cannot fit every aircraft, so you need to keep changing that thing. So this leads to a huge increase in the cost, and also production challenges are there. And because of the loss of vertical tail, the controllability becomes a problem. Of course, these things, most of them are bombers, where they are not expected to get into any kind of dogfight, where they need to have a very, very high sustained turn rate and a 10 turn rate. So it's okay, because most of these bombers are escorted by extremely agile fighter planes which take care of the thing. But however, controllability is an issue which needs to be addressed. And the overriding requirement for any future aircraft, of course, is the affordability. Okay, one of the things which I did mention earlier is the cost of such aircraft. It's reported the B-2 bomber, which I showed a picture of, it costs close to about $2 billion US. Okay, so that's an awful lot of money. So because of the cost, that means even a US Air Force may have only a few tens or twelves of that. Indian Air Force, kind of small country like ours, cannot afford to have one of them. Just imagine, let's say you have two B-2 bombers and for some freak reason they get shot down or they lose control and crash on themselves. $2 billion is down the drain. So this is something which one needs to take care of. It's not very affordable. And that's the reason not many of them are around. Size reduction, as I mentioned earlier, is one of the best ways to try and reduce the RCS at a minimal cost. For example, if you see the outer picture, F-22, a lot of RCS design features have gone in, but Eurofighter 2000 is much smaller. Similarly, Rafale is smaller. So because they are smaller, both are with less wing area and large fuel capacity because of delta wing. So they hopefully have a lesser radar cross section than a conventional same size but traditional aircraft. Of course, these, as you can see, both Rafale and Eurofighter 2000, stealth has not been a design driver. It has been an after fitment, as I said, after delivery fitment. So coatings and you identify hotspots and then take care of that. The aerodynamic problems posed by stealthy aircraft, especially if they are inherently unstable, you want to ensure that the stability of the aircraft is minimized so that
it's easier for it to be able to, or a lesser trim drag penalty. Stability and control due to reduction or removal of control surfaces and the limited area of control surface, all ensuing from stealth configuration. So these are all challenges. In the traditional aircraft, you design a horizontal tail and a vertical tail with the standard tail volume ratios and with the intention of controllability and control authority and whatever else, things like that. But here, in such aircraft, the stealth aircraft, the design consideration of the driver is minimizing radar reflection. So you may end up with a smaller than required control surfaces, which means your controllability is pretty limited. The need for tailless designs places a great deal of emphasis on flight control systems. Usually, and the flight control systems are nothing but a system containing computers, actuators, programs, and a huge aero database based on which the decisions are taken, all on board. Because of the lack of some other control surfaces, one way which has been addressed is thrust vector controlling, and that is basically deflecting the nozzles to be able to achieve a better controllability. So F-22s, currently F-22s have two-dimensional exhaust nozzle, meaning they can only pitch up and down. They are used for signature results. They are, of course, 20% heavier than a more expensive equivalent 3D thing. So, as I said, the cost becomes an issue here too. Inlet duct positioning and shaping due to health requirements adversely affects the engine performance. 100% line of sight blockage to the engine phase to reduce RCS requires engine phase offset at least 0.7 to 1.5 diameters of that from the inlet flow. Basically, you are shifting the engine from at least 0.7 to 1.2 diameters away from the inlet thing. So this means a long duct means losses in stagnation pressure, total pressure recovery, and then increase markedly in the throat flow instabilities, and this can lead to different kind of scenarios. So when the engine does not get the amount of airflow and the total pressure loss is larger than acceptable, this leads to loss of available thrust due to air inlet and nozzle shaping. When the engine itself, a simple engine can give you a thrust, let's say 100 kilonewtons, but once installed in such an aircraft, it may have a much lower thrust. What is called installed thrust can be lower because of whatever has been done, especially with the RCS and things. There's just a picture to show you the kind of total pressure loss one would expect if there are different kinds of shapes and other things. So this is just a pictorial thing which I just picked up from a textbook, and of course this depends on Mach number. At very low Mach numbers, it's no big deal. The total pressure loss is very, very low. But as the Mach number increases, which of course it would because we are dealing with combat airplanes, and close to 0.6 to 7, you can see small changes in the intake duct leads to significant loss in total pressure. And total pressure loss at the engine phase directly relates to the thrust loss. So most of the material I have used, none of it is mine. I have no claim for originality is made here. Most of it is collected from different papers, textbooks, and also from a small article written by Professor Mason from Virginia Tech. Of course, it's late Professor Mason because I think he has passed on. And he has a nice description called 15 Minutes of Stealth in Aircraft Design. So most of the material I have used in this talk are actually from open domain literature, and no claim for originality of anything in such kind is made, and this is done only purely for educational purposes to help the students to be able to have a quick review of different kinds of techniques followed.